Welcome to today's edition of Rohde Schwarz 35. The subject for today is Modern RF Frontend Test Designs for 5G radar and satellite communication. My name is Markus Lörner. I'm a market segment manager for RF and microwave components. Here we see a classic diagram of the RF section. Data comes from the baseband, goes through some signal processing to be followed onto the modulator and the frequency up conversion. Typically this is done by a traditional IQ modulator. It moves on to an IF frequency where we have some amplification, filtering, frequency up conversion to the target frequency, and then the final amplification so that it's ready to be sent out through the air. On the next slide we see a modern block diagram of the RF section, which includes already something like digital to RF and beamforming. And we say digital to RF, it basically says there is not really a classic IQ modulator, but this is all done in the data converters. So we have basically an ideal IQ modulator here. For frequencies above 6 GHz, we still are using some up-down converters. The 6 GHz is like a rule of thumb, so to say. Below 6 GHz, data converters are fast enough so that they can do it directly. Above, around about 6 GHz, we are still using up and down converters. And then in the final stage, which is called here RF conditioning amplification, this is where the final stage for beamforming happens. So what we see there is not only an amplification, but also phase shifters, amplitude shifters before we are feeding the phased array antenna. As you can see, the whole concept, even though it includes already beamforming, is more compact than what we've seen in the classic approach. What is enabling this? Obviously, as I mentioned, digital to RF helps big times to simplify the RF front end. It allows to do direct RF sampling in transmit and receive modules. Speeds of the converters are going up, which gives us access to true RF frequencies. So in D2A converters, we see rates today up to 12 and beyond gigasample per second. This allows us, in an example as shown here, up to 4 GHz of RF frequencies. There are others which go to 6 or 7 GHz already. On the ADC side, it's kind of in a similar way, that they are using frequencies going higher and are able to sample up to 8 GHz, for example. What is enabling this? Obviously, the analog part of the data converter needs to support a higher bandwidth, and not only the first Nyquist zone, but sometimes also higher Nyquist zones. That's a very common trick, especially in the ADC environment, to extend the frequency range beyond the first Nyquist zone. The IQ modulation, which is done basically 100% digital, is in the end an ideal IQ modulation. There is no nonlinearity, no distortion based on the IQ modulation, which we see on a classic analog IQ modulators. Obviously, integration is also going on big times on the data converter side. So what we see here is not only single channel data converters, but multi-channel RF sampling transceivers, as they are called. So they include multiple transmitters, multiple receivers. In other words, multiple D2A, multiple A to D converters. All in parallel, all integrated into one chip. The other thing is not only marrying multiple data converters, but integrating it to other technologies. Something like an RF SOC, where it's a combination with some logic capabilities, logical features, and data converters all integrated into one, simplifying the overall system and making a direct link between the FPGA side, which controls everything, and the data converter side. Going to higher frequencies in A to D converters, uses quite often a trick of using not only the first Nyquist zone, but higher Nyquist zones. What does this mean? So for example, we have a data converter which runs at 6 gigasample per second. The first Nyquist zone is by theory up to 3 gigahertz. We can go up to higher frequencies once we go into the chunks of up to 3 for the first Nyquist zones, from 3 to 6, second Nyquist zone, and so on. So this gives us access to higher frequencies. Obviously, as you can see with the red curve here, the sensitivity, the level which is seen by the ADC, is going down. So the quality of the signal to noise ratio goes down. The other thing which you have to keep in mind when you do this approach is that the signal which you want to sample needs to sit just in one Nyquist zone, just in the first, just in the second, and so on. There should not be any overlap, because otherwise the signal cannot be correctly reconstructed. Now, when we want to send out the signal through the air, we need to overcome the free field loss. So typically what we do is we give the signal, before we send it to the antenna, enough power so that on the receiver side it can still be received with a good signal to noise ratio. So the traditional approach here is just give the right technology, to use the right technology to enable high enough output power. Obviously, the higher the frequency, the higher the output power also needed, the more expensive the whole thing gets, and also the more complicated from a technology point of view. So this may not always be the best and most efficient way. There is a lot of work being done today and already in the past, and for sure will be done also in the future, to make more efficient RF front ends. There are different methods to do so. Very often they are using a structure with multiple amplifiers and construct a signal from 2 or more efficiently generated components. There are different types which are used, plus some hybrids, so some combinations of the different technologies, like envelope, outfacing, and Doherty systems. Most of the amplifiers which we see today are based on Doherty structures when we look at those which are applied in our 3G, 4G infrastructure, and also probably in the 5G infrastructure in the first time. What we are seeing now as a new trend is something called load modulated balance amplifier. It has been proposed in 2016, and a lot of research is ongoing to understand the abilities of this new technique. But again, it is using the same concept, basically using a construct signal from 2 or more components. The next step, as I mentioned also in my first overview plot, is phased array. Why are we doing phased array? We'll come to this in a second, but it is definitely something which we are seeing more and more in the industries. So in infrastructure, in mobile communication, 5G, especially in the frequency range 2, so in the millimeter wave range, beamforming is an absolute requirement. Also in frequency range 1, we are seeing massive MIMO approaches with use of phased array antennas. Satellite payloads and ground stations, especially for low Earth orbit systems, are directly on the verge to move to phased array applications, and are starting to use it more and more. We see it at first at the ground stations, but also the first satellite payloads are in operation which support phased array systems. In EW systems for jamming radar applications in the A&D world, phased array is already kind of technology of today and used since quite a while. The idea here is to be able to track and to point the signal into a dedicated direction. Automotive radar is also starting to look into and starting to use phased array applications. Everyone is talking today about beamforming and phased array, but is it really new? No, it's actually a pretty old concept. It was proposed by Carl Ferdinand Braun already more than 110 years ago. He got a Nobel Prize at the time for his work on transferring signals over the air. And while delivering his Nobel speech, he was like, well, everyone knows already for what I'm getting the Nobel Prize. So I want to talk here about something new. He did some work with multiple antennas and found out that when using the signal in the right way and applying it to the antennas at the right format, you can create a signal direction, a beam which goes in one direction. But today it looks a little bit different and more sophisticated. We are using now planar antennas, phased arrays, with a much higher integration. You see on the right side a picture from Renesas, which was done as a proof of concept design for their millimeter wave approach. You see on the upper side the front panel with all the different antenna elements. On the lower side you see the back plane, where there are small ICs driving, in this example, 4 antenna elements in parallel. Much higher density, much higher efficient in order to create such a signal. What you see on the left side is basically the approach where today we do not only want to track one beam, but we want to do multiple beams in parallel. Just think about a 5G environment. You don't want the base station and infrastructure to only be able to support one user. We need to be able to support multiple users, which means we need to create multiple beams at the same time from one antenna element. But why are we looking at those things? Obviously, the higher the frequency goes, the free field attenuation goes up. Here is the Friese equation shown, and what you can see directly is that there is the dependency based on the frequency. Below there is a table with some examples just to give you an understanding, an idea of what we are talking about. We are looking here at 28 gigahertz, and if we see for free space loss, at a 10 meter we are already seeing more than 80 dB of loss, and when we are thinking about 100 meter, more than 100 dB. So this would create extremely small coverage areas. So we need to find a way to get more efficient to cover a certain range and to be more efficient than just putting in huge amplifiers, as they would also be pretty expensive for 28 gigahertz. So the idea here is to say, well, let's point the signal in a certain direction. This graph gives a nice overview. In the end, when you use a classic approach with a wide angle antenna, and the signal which is sent out is basically only received by one receiver, there is a lot of wasted power. While on the right side, we are taking, in this example, 120 antennas and point the signal just to the one person. What we see is that with 120 antennas, we need in total, in sum, less than 1% of power to get the same power to the receiver. Much more efficient, and this is exactly why beamforming is used in millimeter wave ranges. So how is it all done? In the end, we want to use a series of multiple antennas and condition the signal for each antenna. It's all based on the different directivity and the direction of the incident signal with the angle. So And this is the same if we have a transmit signal or receiver signal. In this picture, it just shows a receive signal, but this is exactly the same for both ways. So the phase front of the signal reaches the antenna elements from right to left at different times. At first at right and then later on to the left. And this is kind of the key finding. So what we want to do is to compensate for the time difference, which when we translate this, the time difference between the different elements to the RF signal, it's basically a shift in the phase of what we receive from the same signal. So what we have to do is to apply some phase shifters behind each element. And when we send out a signal with this approach and apply a certain phase correction for each of those antenna elements, we get already a certain main lobe in one direction. And based on the phase shifts applied to the different antennas, we can steer the beam in different directions. Unfortunately, this approach still gives us pretty high side lobes. So side lobes means it's unwanted power, it's unneeded power, it's basically energy waste. How can we get those down? And what is found out is to apply a certain weighting behind each antenna element. And this, in this example, gives us already a 10 dB improvement for the side lobes. The dimension of those phased array antennas are basically following the target frequency. The wavelength of the frequency is the key dimension and is the defining structure for the antenna elements. The element spacing, for example, need to be smaller than half of the wavelength. Because if it is larger, the beamforming will not really work anymore in the right way and an unwanted main lobe will appear, as shown in the graph in red. So what we can show is that as frequencies are going up, dimensions are going down. That also means that all the driving network behind it needs to supply it. But on the other side, if we are going closer with the antenna elements, there is also some crosstalk in between already on the phased array antenna. With regards to beamforming, there are different concepts, how to drive the antennas. The classic approach is called analog beamforming. What we are doing here is that the signal chain is the same as in the classic way, just that we split the signal in the end and apply phase shifters, probably also some weighting for each antenna element. Works nice, works straight out. Has a major shortcoming. In this approach, I can only create one beam in one direction. If I want multiple beams, I have to do the same thing over and over again for another beam. The other side, it is called digital beamforming. Digital beamforming is, instead of using phase shifters on the RF side, we are doing all of this already pre-processing on the digital way. So we split off the signal already on the digital side, apply phase offsets for a beam, and then feed it to the antenna. As you can see, the major downside on this approach is that the RF chain needs to be separate for each antenna feed. But the digital baseband processing allows us not only to calculate the components for one beam, but for multiple beams. So we can not only do one, but multiple beams at the same time. And the limitation is really just based upon the calculation power of the baseband processing in theory. This is a concept which we are seeing very often in sub-6, 5G approaches where they are doing massive MIMO and beamforming. This is the most flexible approach as it gives us 100% digital reconfiguration of the phased array antenna. But in order to get to a very high number of antenna elements, it's probably not the most efficient. why hybrid beamforming is becoming popular, especially on the millimeter wave side. It combines both worlds. It combines the digital baseband processing for being flexible and offering all the benefits of applying multiple beams at the same time. And on top of it, applying also analog beamforming in order to increase the number of antenna elements in a cost-efficient way. So you could say hybrid beamforming takes the best of both worlds. Obviously, as we could see before, phase tolerances is an important thing to look at, because if there is a phase variance, the signal is not perfectly steered anymore. In an ideal world, as we see it on the left side, the signal is only sent really to one user, and all the other users are ideally in the nulls of our beam for the from the antenna. If there is some phase tolerance, the nulls are not really nulls anymore and they are looking at different areas. So the other users see also some signal from that one, which creates a higher noise floor for them, making it harder for them to keep up with their connection. So what we are seeing is that there is typically an adaptive self-calibration in operation. What are the different design pain points in the system? Obviously, on the digital side, it's important to make everything as clean as possible with regards to the power supply and the signal on the digital side. And obviously, it's clock distribution. Same is true with the clock also for the data converters, but when we're doing multiple of those for digital beamforming, it's important to make sure that the timing between the channels is in line. The filter, that's a classic approach with filter steepness and ripples and group delay. So those are nothing different than known. Same is true for the up and down converters. The only thing which is of importance here is that when we apply also digital beamforming or hybrid beamforming, to control the phase on the RF, it is done on the digital side. So we need to understand how phase from the baseband or from the IF signal translates to the phase of the RF system. This needs to be understood and being incorporated on the digital beamforming. Last but not least, the RF conditioning and amplification is basically a classical front end. So we are seeing here all the thermal requirements, we are seeing the amplification requirements, and based on using phase array antennas with beamforming, there is a lot of variance and a lot of focus on the phase and level accuracy over temperature and frequency necessary. Last but not least, the antenna. With beam directivity, how accurate can we steer the beam, how fast can we do it, what type of crosstalk do we have, and how can we make in an efficient way measurements on an over-the-air system when we have no access to the RF in a conducted way anymore. In hybrid beamforming applications, we have typically the baseband and the digital beamforming, okay? And then on the other side, we said we are combining it with analog beamforming for being more efficient and in order to drive up the antenna elements. This is typically done with highly integrated beamformer ICs, as they are called. Here is an example of a beamformer which is made for a radar application in the X-band. It looks very similar also for 5G in the millimeter wave range. What are we doing is we are sending one signal in, we have one connection to the main system, and the signal is then split off in this example into 4 channels. And each of those channels has a separate transmit and receive path. Obviously, all of those transmit and receive paths need to be fully calibrated and understood their behavior of the phases and levels across the channels, across temperature, so that you can make really good beamforming and to have a stable system over temperature. That's also why they typically have temperature sensors and are feeding those information back on the controlling device. As those are multi-port devices, it's wise to understand the effect of the crosstalk between all the different ports. To really make measurements on all the ports at the same time, so that you really see when you want to get a certain power of antenna 1, how much is going on at antenna 4, you need to be able to measure at all ports at the same time. A true multi-port network analyzer with a reflectometer, so a full VNA port behind every connector, is the only way to get access to all of this information. And there are variants which go of those beamformers not only with 4 antennas, probably dual polarized, so we have already 8 antenna connections plus the RF in-out, or even up to 16 antenna elements. So multi-port VNA, which is scalable and supports up to 40 gigahertz, is able to do the job. On the other side, with the up-converter stage, we mentioned it is important to understand the relative phase behavior from the IF to the RF. To do those measurements, those were in the past pretty complex and needed additional measurement mixers. Not so with the new VNA ZNA from Rohde Schwarz. It is able to have a coherent mode, even so between different frequencies. And it is able to understand the different phase relationship between the two passes. And with its multiple LOs, it also offers a high-speed improvement over classic measurement approaches. In the beamformer, obviously one of the main parts is the output amplifier for each channel. Those can be measured in the same way as a standalone amplifier. With the vector signal generator R&S SMW200A and its signal and spectrum analyzer R&S FSW, you have a tool set which is able to make those amplifier measurements, no matter which standard, in an easy and integrated way, and also even offering support for digital pre-distortion and any kind of a standard from radar applications, satellite signals, or 5G with up to higher frequency bandwidth, up to 2 gigahertz of bandwidth and millimeter wave range frequency coverage. Going on to the next step with the antenna and probably even antenna in package systems, obviously measurements need to be done in kind of a chamber for doing over-the-air measurements. Rohde Schwarz has developed a whole series of different OTA systems, not only large ones, but also very compact versions, which are able to give you far-field condition in a lab size in a mobile environment. These systems enable, on one side, characterization of the antenna capabilities, so basically giving you antenna structures where you see the beamforming and what they can do, but also allow performance measurements like EVM in an over-the-air environment. When you make measurements in an over-the-air environment, it's important to understand at which distance you need to be, as there are different areas. Obviously, in the far field area, measurements can be done like in a real world environment, because this is what is happening in the real world scenario. In the radiated near field area, you can make measurements on antenna characteristics. It is not so accurate here to do any more EVM or performance measurements. And obviously you want to be away from the reactive near field region. in order to shrink the sizes of the chambers, there is a system called compact antenna test range. It's not using a direct feed, but it uses a dedicated reflector, which is fed by a feeder antenna and creates a quiet zone in a relatively small chamber size. It gives a larger quiet zone than any other process and enables to measure not only small devices at higher frequencies, but also larger devices, as the size of the radiating aperture has a huge influence on the distance which is needed. For doing over-the-air power calibration, we are also offering dedicated integrated power sensors with an antenna, which offers calibration methods and high accuracy as known from power sensors. So what we can say as a summary: with phased array antennas and highly integrated systems, a lot of integration is happening. New components are coming to the market, like beamformers, and actually they are already starting to go the next step to not only integrate all the different electrical functions, but also integrate antennas. So this is where this antenna in package, antenna and system comes from. So what we are seeing is that a lot of testing shifts from conducted to over-the-air environment. More information can be found on the Rohde Schwarz website. Here are just some examples of the different offerings. With this, thanks for watching and stay healthy.